We've been looking at the exponential function. Now we've seen how we can differentiate it. So let's see how we use it in rates of change problems. Some typical ones. Now, one of the most classical examples of rates of change with exponentials is the idea of growth and decay. It starts with a very, very simple assumption, and that's that the rate of change is going to be proportional to the actual population itself. So in other words, the more that you have, the more that will be born, the more that will die. So it's something like this. The rate of change of the population with respect to time will always be some constant times the population itself. So that's the idea. Now, it's a very, very simple model at this stage. The solution ends up being this. P equals AE to the KT. Now, it is okay for our purposes. As soon as we see what's called a differential equation where it's equal to some constant times P, we can jump straight to the answer and say, well, we know P equals AE to the KT will be a solution to this. Let's have a look at some HSC ones then. So back in 2015, they were interested in looking at the amount of caffeine in the body. And they said, well, look, it obeys this particular model, that the rate of change of caffeine over time is equal to negative 0.14 C. So negative tells me the amount is decreasing over time, and it'll be 0.14 of C, where C is the amount of caffeine, and it's measured in milligrams. Time for our purposes for this one is in hours. So you remember I just said we can just jump to the solution. So what they often do with these is sort of reverse it. Rather than saying solve the equation, they give you the solution and say show that this solution works. So that was the first part to this question. Solution C equals AE to the minus 0.14 T. Okay, well all we've got to do is differentiate it and show that it satisfies the minus 0.14 times the C itself. So there's the equation they've given us. C equals AE to the minus 0.14 T. Now A is just a constant number. If I differentiate the exponential, we know we differentiate the power. In this case, it's a nice linear power. So differentiate minus 0.14 T with respect to T, we'll get minus 0.14. So our derivative becomes minus 0.14 AE to the minus 1.4 T, but hang on a sec, AE to the minus 0.14 T, that's what we said C was equal to. So yes, indeed, that is equal to minus 0.14 C. So yes, this does work for our model. Okay, now they've told us when T equals 0, so initially we know there's 130 milligrams of caffeine in Lee's body. Find the value of A. So what was A? It's really just a substitution question now. So when T equals 0, we know C is 130. We just said the solution was AE to the minus KT. So it's going to be AE, well, times 0. So it'll be AE to the power of 0. E to the power of 0 is 1. So A turns out to be 130. Well, how much is going to be there after 7 hours? How much of this caffeine is gone? So when T equals 7, but we now know A is 130. So we're substituting into 130 e to the minus kt, well k in our case is minus 0.14, t they've told us is 7, better calculator work, I've done it to one decimal place, 48.8, so we know 48.8 milligrams remain. So what is the time taken for the amount of caffeine in the body to halve? So when is C65? So half of the initial amount. Now what ends up happening, no surprise here, we're going to solve this exponential equation and we end up with the exponential equals a half. Well, makes sense because we're saying when is it halved? I'll make t the subject of that. So to undo the exponential, we log both sides. Notice it's the natural logarithm here because we're talking base e. There's the exact value, but I suppose we're more interested in an approximation for this one. So we get about 4.95105. So about 5 hours. It will halve.